Here is the last part of proposition 5.5.2 in your book. So as usual, we start with a metric space. And a compact subset of the metric space. And in this one, we're going to let f be a function from x to z, where z rho is another metric space. And we're going to require that f be continuous. Then the image of f of k is also compact. And the proof, let's write that out. Let's let G be an open cover of f of k. So remember that means that f of k is contained in the union of all the sets in our collection G. And each G in our collection, our cover G, is an open subset of f of k is in Z, so G had better be open. Then by proposition 5.4.3b, if G is in G, then f inverse of G, that's an open subset of X, is open. Remember, proposition 5.4.3b says a function is continuous everywhere if the inverse image of all the open sets is open. And if we pick a point in our compact set K, then f of k is in f of our compact set, which, remember, we've got a cover, so f of k has to be in one of our open sets G, which equivalently means that k on its own is in f inverse of G for some G in G. So this collection H, that's the set of all f inverse of G, such that G is in our open cover G, is a collection of open sets in X that cover K. So H is an open cover of K. And since K is compact, so our new open cover H has a finite subcover. H1, which is a subcollection of H. Now we need to build a finite subcover of G. For each for each H in H1, pick one set G in G such that H equals F inverse of G. And I want to emphasize that you might indeed have to carefully pick just one H. There might be a bunch of different G's such that F inverse of G equals H. But so you just pick one of them. And let's let G1 be the collection of those G's. Then G1 is a subset of G, and G1 is finite. We've picked it to have the same number of elements as H1. And if we've got some element Z in F of K, then Z equals F of X for some X in K. So X is in H, which is F inverse of G. Since H1 is an open cover, X is in one of the H's. For some H in H1. So F of X equals Z. X is in F inverse of G if and only if F of X is in G for some G in G1. Thus, we have that G1 is an open cover, a finite open subcover of G. So we've seen that every open cover has a finite subcover. So F of K is indeed compact. We're now in a position to generalize a theorem from section 1.5. We're now in a position to generalize the extreme value theorem. That is theorem 1.7.6. So so this says that any continuous function on a compact compact set attains its maximum and minimum. This is how it's usually stated. A continuous function on a compact set attains its maximum. Let me write this more clearly. That is, let's let X D be a metric space. And K a compact subset. F is a function from K to the real numbers. You want to be mapping into the real numbers. You don't want to be mapping into an arbitrary metric space, because in an arbitrary metric space, you don't, really have maxima and minima. You don't necessarily have a biggest element. And so we've got a continuous function from our compacts or our compact subset of a metric space. Then there are two things that are true. The first is that if you take the supremum, if you take all the f of x's where x is in K, the supremum, the least upper bound of that, it's finite. It's less than infinity. And moreover, there is a point, let's call it M in K, such that f of m is this supremum. That's the supremum of all the f in x, f of x where x is in K, and therefore this is in fact not only a supremum but a maximum. Maximum in our terminology is a supremum that's actually an element of the set. You can write out a proof of this directly from the definition of compact set. You can come up with the right open sets to cover K to get that you're bounded, and once you've got that you're bounded, you can come up with the right open sets to show that you actually achieve this bound, but you can also prove it very quickly using proposition 5.5.2. So we'll do that. So by the thing we just proved, f of K, subset of the real numbers, is compact. And then by proposition 5.5.2a, we have that f of K, which is compact, is closed and bounded. So that means there is a natural number m such that negative m less than or equal to f of x less than or equal to big M for all x in in K. So we've seen that F is bounded. So now we just need to show that there's a point that achieves its bound. And if you think about it, we could have proven back in section 1.6 that the supremum of a closed set must be an element of the closed set. The supremum of a set of real numbers always has to be a limit point. Let me write out why this is so. So let's let big M be, let's let big S be the supremum of the set F of K. That's the supremum of the set of all the F of X's. And then for each natural number n, we've got that S minus 1 over n is less than S, is not an upper bound. So there is an xn in K with f of xn bigger than S minus 1 over n, but it's always less than or equal to S by definition of least upper bound. So f of xn, this is a sequence in f of k. F of xn is converging to S. F of k is closed. So S must be in f of k. So S equals f of m. Also, this is also known as the supremum of the f of x's for some m and k. And that is what we were trying to prove. Here's a similar proposition. That is, you can similarly prove it using just proposition 5.2, maybe. All right, we'll call it corollary. This generalizes proposition 2.3.9, at least in some cases. Proposition 2.3.9 says that if you've got a continuous function defined on an interval, maybe open, maybe closed, maybe half open, maybe bounded, maybe unbounded, then its inverse must also be continuous. You are going to prove on your homework or the exam, let's let XD be a compact metric space. So the compact subset K, we're going to take as the entire set. Zero, another metric space. And f, a function from x to z, is a continuous bijection. You should have seen in Transitions to Advanced Mathematics that every bijection has an inverse. And the content of this corollary is that F inverse going from Z back to X is also continuous. Let's recall a couple of known facts. So from homework 12, we have that if the metric space KD is compact, and that means that K, which is a subset of K, is compact. That is, satisfies the conditions of definition 5.5.1. So this set K is compact in AD, and I think I'll just use if KD is compact or is a compact metric space to mean that from now on. And X delta is a superspace. Then K is compact in X delta. So being compact doesn't depend on what space you're in. Then let's put this together with proposition 5.5.2a. If KD is compact, or rather, proposition 5.2a says that if K is compact in X delta, but we know that that just means that KD is compact and X delta is a superspace. Then K is closed in X delta. Converse is not true. You should recall from homework 8, if KD is closed in all superspaces, which is true if K is compact, then K is complete. And the conclusion is that all compact metric spaces are complete. And this is not an if and only if statement. So let's let K be the real numbers and D be our usual absolute value metric. Then this is a complete metric space. We went to an awful lot of trouble last semester to prove that the real numbers are complete. It's pretty much the whole reason why we bother with the real numbers and not the rational numbers. But we saw in the last video that the real numbers are not compact. You can take you can try to cover it with, say, intervals of length 2. You obviously need infinitely many intervals of length 2 to cover up all the real numbers. So if we want to turn homework 13 into an if and only if statement, we're actually going to have to put something more onto it. So let's recall the next part of proposition 5.5.2a is that if K D is compact, then K is bounded. Okay, so is that enough? Are all bounded complete metric spaces compact? And the answer, unfortunately, is no. We're going to need a little bit more, but let me give you an example of why this is true. Let's let K be the natural numbers, or your favorite infinite set, and D be the discrete metric. And then K is bounded. In this metric space, it's not bounded under the usual metric. That's one of the strange things about the discrete metric, distance from x to y. Remember, under the discrete metric is always at least 0 or 1. So the diameter of K is 1, or K is contained in the ball centered at x of radius 2, or 1.5, or any number bigger than 1, or you can actually make it 1 if it's the closed ball, and this is true for any x in K. K is also complete. And by examples 5.2.2c and 5.2.4c, K is complete. So under the discrete metric, the only way to be a Cauchy sequence is to eventually be constant, and the only way to be a convergent sequence is to eventually be constant. So of course, all Cauchy sequences are convergent, and that's precisely the definition of complete. But an infinite set under the discrete metric is not compact. We worked that out in this example out in detail at the start of the last video. The set of all balls centered at a point of radius 1/2 is an open cover. With no finite subcover. So it looks like being complete and bounded is not enough to be compact. So let's write down a definition of a concept that is a little bit stronger than being bounded. And we will show eventually that being totally bounded, which I'm about to define, and complete is enough to be compact. So K, a subset of X, is totally bounded in the metric space XD, and being totally bounded is a lot like being compact or complete or even regular or bounded. If whether you're totally bounded in XD just depends on whether you're totally bounded in yourself in KD. This is true if for all positive radii R. So remember, a bounded set, you can fit it inside one ball of a possibly very large radius. Well, totally bounded, we want to fit K inside balls of arbitrarily small radius R, but we don't want to put K in one ball of radius R. So totally bounded means you can always fit K inside either finitely many balls of radius R, possibly very big number of balls if R is small, but finitely many. And you'll prove, probably I'll make this an exam study problem. So this is exercise 5.5.4 in your book. If KD is totally bounded, then it is bounded. But the converse is not true. Go back, we can go right back to this example up here, the discrete metric on an infinite set. So if D is the discrete metric, and K is infinite, then KD is bounded, but not totally bounded. For example, you cannot cover KD by finitely many balls of radius 1/2, so total boundedness doesn't work with R equals 1/2. And it's not too hard to show that all compact sets are indeed totally bounded. So you just pick your positive radius, and then the set of all balls centered at point x of radius r such that x is in K is a collection of open sets, and it obviously covers K. Every point x in K is in one of these balls. It's at least in the ball it's centered at. So there is a finite subcover which we can write as Bx xj. Let's not use K. And if you write out what it means to be a cover, that's precisely that K is in the union of these balls for some points x1 through xn that have to be in K because our cover started with balls centered at points in K. This video is getting long, so I will give you a fairly quick proposition, and we will get into the converse. We'll show that complete plus totally bounded is enough to be compact next time. So this proposition says that if the K D is totally bounded, so in particular if it's compact, but more generally, then it is separable. And if you've forgotten what that means there is a countable set which I'll go ahead and call Q, subset of K, such that the closure of Q is all of K. If X is in K, then there is if X is in K and R is a positive radius, then there exists a Q in your countable subset Q such that X is in the ball centered at Q of radius R. And the proof is pretty quick. So let's let x1, x2 up through xn be points in K such that K is contained in the union of the balls centered at xj of radius 1. And because K is totally bounded, I know that these numbers these points xj exist. Let's actually call this index n1 instead of just n. Let's let x sub n sub 1 plus 1, x sub n sub 1 plus 2, up through x sub n2. These are going to be points in K, be such that k is in the union, you could start at n plus 1, or you could start at 1. It won't hurt the balls of radius 1/2. So, and then continue. This constructs a sequence that's contained in K, such that if epsilon is greater than 0, then epsilon is less than 1 over n for some n in n. So actually, let's call that epsilon less than 1 over m for some natural number n. So k is contained in epsilon is greater than 1 over m. So k is contained in the union up to n sub m balls centered at xj of radius 1 over m, and then epsilon is bigger. So if x is in k, then x is in balls centered at xj radius epsilon for some xj. And since there's a sequence of the xj's, obviously there's countably many of them.